Go back to the morning show coming up on 6:50 this Wednesday. That only means one thing. It's Wise Guy time. Our very own U of I physics professor Mats Selen is back in. Mats, thanks for coming back.
Well, it's forever since I've been here.
It seems
been a long
like
time, and the last time we did something about magnets, as I recall, and it was made some sound and things like that. And I realized, there's some very cool stuff you can do with just the fact that the Earth itself is a magnet.
Okay.
And it's kind of interesting, and it's something that kids can do. So I wanted to show you some of this stuff. It's pretty neat, and people have known for quite a long time that there's a north and a south in terms of sort of a magnetic north and south to the Earth. If you pick up a compass, if you're out lost in the woods, you can go like this, and you can go, ooh, look, north is that way, and maybe you'll get out of the woods before the wolf eats you, maybe you won't. And people have known this for a while, and the very simplest compass you can make is if you just take a magnet, and this little metal thing is a little magnet I just found in my office.
Okay.
And if you just float it on something in water, so watch what this thing does, it'll just zoink. It just aligns itself. So it turns out that the long flat end is north on this particular magnet.
Oh, okay.
Okay, so it doesn't line the skinny side, so that it's north this way, in other words. But if it turns pretty quickly if I just let this thing go.
Yeah. Boom,
just like that. So it's exactly the same way that this thing works. And so I thought I would talk a little bit about how this actually works on the Earth, because what this means is that this magnet, it must be attracted to some other magnet in order for it to line up that way.
Right.
And we know if you play around with bar magnets, we've all done this in school.
Sure.
If you hang on to this thing, right, the north end will sort of point north, but I can fool it. I can take another magnet, and I can see that the north end of one magnet is attracted to the south end of a different one, right?
Sure.
So and it's repelled by the north part. So the north poles of two magnets want to get away from each other. If you take a south and a north and you get them close, they want to attract. Okay. So now right away that tells you something funny, because if this is the north pole of a magnet right here, and it is, and it's pointing north, I thought north was supposed to repel north. So how do you explain that?
That's why you're here.
Oh, is it? Okay. Well, so actually the explanation for that is that the Earth, the north pole of the Earth, the geographic north pole, is actually the south magnetic pole of the Earth if you think of it as a magnet.
Oh, I got you.
So the Earth, basically the Earth, now you get to see my fantastic art skills.
Cool.
Okay, so here's the Earth. Okay, we have north stuff here.
Right.
And if you want to think of the Earth as being a magnet, let me draw the magnet in like a bar magnet that we just had.
And we hold this way.
Like this.
Right.
So the bar magnet part would have the north part down here and would have the south part up here. Okay. So the south magnetic pole is the thing that's close to the north geographical pole, which is sort of interesting. It sort of makes sense. Okay. Now this magnet is not perfectly lined up with the Earth either. Okay, it's sort of tilted a little bit, and in fact, this magnet isn't really even a bar magnet like this, obviously, because the Earth is just a big fat round thing or spherical thing. And so, how would you have a bar magnet like this? And that's actually a very interesting question. So let me actually show you what we know about the Earth's magnetic field.
Okay.
Okay. One thing that's very, very interesting is if you look. I'm going to turn this a little bit sideways. I wonder if you can get that on camera.
We got it.
This is like a magnet needle. And it tells you in the vertical plane where north is. And you'll notice that north doesn't sort of just point straight north along the road.
Right.
It kind of points into the ground.
Down, sure.
Okay? Which is sort of weird. And how the heck does that work? And the reason that it works that way, if you want to understand the behavior of a bar magnet, do we have a minute?
Yeah, sure.
Okay. All right, fine. So if you look at this thing, all right, what I have here is a little thing, if you can zoom in on it, maybe, okay? It's got there we go. It's got a bunch of little arrows. Okay, and the alignment of those arrows tells you the direction of the magnetic field lines. Okay, and so you see that they kind of come together at the north and they come together at the bottom at the south, but along the sides they're a little bit parallel. But you also notice that they sort of poke into the side of the magnet, right? Like well, I'm doing this pretty badly, but right there. Okay, they're coming in at an angle. They're not just going parallel all the way. And so what happens is, if this is our magnet, which is the Earth, the magnetic field lines kind of go like this. Okay, but some of them are coming out through the surface, and so they kind of dive into the surface of the Earth at an angle like that.
Makes sense.
That's why it kind of pokes down like that.
Cool.
Okay.
We are versed in magnets. What are we going to talk about in 30
Okay,
minutes?
when we come back, I have an electromagnetic way. I'm just going to try to explain how the Earth makes this magnetic field and how we can cancel it out, because when we sometimes do experiments in labs, we don't want that magnetic field there, so I have a little gadget to do that.
Very cool. We'll show you that when we come back. Mats, thanks for coming in.
Oh, anytime.
All right.